So hello all, welcome to this next lecture. In the previous lecture, we have introduced what is the different bands of microwave frequencies that we can have. Now today, let us discuss about the general structures that are used for guiding the microwave signals, which are nothing but waveguides. So as I told you, microwave frequencies are 1 gigahertz to 1000 gigahertz frequency. So because this is a high frequency, the energy carried by the signals is also high. So in such cases, the normal or the conventional transmission lines that we use, such as coaxial cables or the twisted pairs, they are of not much useful. So we require special structures that can transmit or that can carry the microwave signals without losses. So such kind of thing is done by a structure called as waveguide. So what is a waveguide? So waveguide is basically a metallic a waveguide is basically a metallic structure that is used to guide the wave along its walls. So it is a metallic structure, a hollow metallic structure that is used or that can guide the wave along its walls, along the walls. Okay, so such kind of structure, right, is called as a waveguide. So it is basically a metallic structure which has a hollow space inside. For example, if I consider a general case, a parallel plane waveguide. So I have two metal conductors, right, placed parallel to each other like this, and inside these two conductors I have hollow space. Right now, the EM wave will be propagating through, or this structure will guide the EM wave to propagate through it along the right with the help of the reflections along the walls. Okay, so the wave gets propagated inside this structure. So a metallic structure that is used to guide the wave along the space inside the inside the waveguide or inside the structure is called as the waveguide. Okay, so simple definition, right? So how do you construct a waveguide? As I said, we need some metallic structures, metallic conductors. Okay, and these two metallic conductors should be separated by a dielectric. Okay, so inside that either air can be present or vacuum can be present or any other media can be present. Then only it will be able to transfer the signal. So as we told, waveguides were also basically a type of transmission lines. So we know, right, for a transmission line, if you want to get a transmission line, we need two conductors separated by a dielectric. So same is the case here. So if you want to construct a waveguide, we need two metallic conducting plates, and those two should be separated by a kind of dielectric, which can be air, vacuum, or anything. Okay, so these kind of structures will help us in transferring the microwave frequencies or microwave signals through them without much losses. Okay, so this is the simple right waveguide. Now in general we have three four wave guiding structures, so we can use right. So the most general case, right, the most general type of the waveguide that we refer to is a parallel plane waveguide. So this is only a theoretical one. So as I just told you, it is constructed by placing two parallel planes, okay, or two metallic planes, okay. So one above the other like this. So I have right. This is one plane and this is one plane. I place them like this, okay. So parallel to each other. Okay, so like this is the structure that we have. So these are only theoretical structures because we generally, right, as you can see, the other two are open, right? So it is open. So, right, the losses will be high, and hence we generally don't have a practical waveguide which is of parallel plane type. Okay, so this is only a theoretical case. So other than this, we can have a rectangular waveguide. So a rectangular waveguide, so which is formed with in the shape of a rectangular box like this. So you have right structures like this. So this is my rectangular waveguide. So a rectangular waveguide simply looks like, as we discussed, looks like a box like this. So right, I have okay. So these are the four parts of the rectangle. Okay, you can assume like a textbook like this. So this is the thing, right? So this is a rectangle, right? Inside this, okay. So I have a conductor here, I have a conductor here, I have a conductor here, I have a conductor here. So there are four conductors, okay. So I form a box with the help of four conducting plates, okay. And inside this box, the space is hollow, okay. There is no any kind of material present inside, so it is air filled or vacuum filled. You can assume it as air filled, okay. So in this kind of structure is called as a rectangular waveguide. Similarly, we can also have a circular waveguide. So a circular pipe, okay. So just like this is an example. So I can have a with the help of a conducting material, I form a pipe, and inside this pipe everything is hollow. So such kind of structures are called as circular waveguides, okay. So these circular waveguides are also can be used to transmit the electromagnetic wave or microwave through it, okay. So parallel plane waveguide, rectangular waveguide, and circular waveguide, these are the most popular types of the waveguide structures we have, right? So yeah, just now we discussed what is a waveguide, right? So it is a general structure made up of metallic plates, so that is used to transmit, okay, microwave signal through it, right? Now, how does this transmission occur? What is the principle of transmission? So the next thing is, what is the principle of transmission? Okay, or how does the microwave signal gets transmitted through the waveguide? Principle of transmission, okay, through the waveguide, okay. So basically, right, when we discuss the electromagnetic theory, we have studied something called as the oblique incidence and normal incidence concept, right? So we studied that whenever the electromagnetic wave, right, is transmitted from one media to the other media. So let us say the intrinsic impedance of medium 1 is neta 1 and intrinsic impedance of medium 2 is neta 2, okay. So if I right, there are two ways by which I can launch the signal from the medium 1 into the medium 2. So one way is to do like this, so using an angle of 90 degrees, okay. So if this is my plane of incidence, okay, so if this is my plane of incidence, then I am launching the signal exactly like this, okay. So this kind of incidence is called as normal incidence, correct. So this kind of incidence is called as normal incidence, okay, where you are launching the signal exactly perpendicular to the plane of incidence. So it is making an angle of 90 degrees or 0 degrees. You can assume either way. Okay, so like this. Now, in this case, this is called as normal incidence, and we studied that in the normal incidence case, there will be some part that gets transmitted without change. So if this is my wave, right, and if this is my E bar component, and this is my H bar component, okay. So this is my E bar component, this is my H bar component. So if I launch this wave, so there will be no, some part of the signal will transmit through the medium 2 without any change in angle, okay, right, and some part will get reflected, right, some part will get reflected, okay. So like this, so this is the reflected part, so it will get reflected back with 180 degrees phase shift, and some part will go through without any change in the phase shift of the original signal, okay. So that is 0 degrees phase shift. So this kind of incidence is called as normal incidence, okay. Next, if I launch the signal, right, if I launch the electromagnetic wave from the medium 1 into the medium 2 at an angle other than 90 degrees, okay. So if this is my plane of incidence, so here I am launching it with a theta, with an angle theta, which is not equal to 90 degrees, okay. So this is my normal incidence, this is my right, okay. Now I am launching the electromagnetic wave, okay, in this way or in this way or in this way or in this way, okay. So any other angle, right, other than the 90 degrees angle is called as the oblique incidence, okay. So it is called as the oblique incidence. So you are launching obliquely, okay. And whenever you launch obliquely, that is whenever you launch it with a certain angle which is called as theta I here, theta I, the angle of incidence. So in this case, there are two things that can happen, right, will happen, okay. So first thing is, so if we assume this, okay, So generally the wave should, right, if this is the normal propagation of the wave, right, so without any phase shift, 0 degree, if there is no phase shift, then the wave would have traveled in this way. Okay, so it should go like this. But now what happens is, so there is a mechanism called as refraction, and the wave gets slightly shifted, phase shifted, and it will change, it will bend its angle. So right, there is a phase shift happening in case of the reflection. Okay, in case of the right second media, going into the second media, which is called as the refraction. Okay, and at the same time some part of the signal also gets reflected back into the original medium also, which is what we call it as a reflection of the wave. Okay, so whenever I launch an electromagnetic wave with the normal incidence, two things will happen. One, some part of the signal goes into the original medium, okay, which is called as reflection, and some part of the signal will go into the second medium, okay, with a slight phase shift, which is called as refraction. So there is a refraction. Okay, so earlier it was only transmission, right? In the case of normal incidence, it was only transmission, so the wave would have gone as it is, right? But now what is happening, right? The wave is not getting transmitted as it is, it is also taking a phase shift. Okay, so phase shift is of the signal is happening, which is called as a refraction, and a complete, right, case will happen. Okay, right. Now now if, okay, if we consider a special case, okay, where, right, if I launch it at a particular angle, right, or otherwise if I consider a special case where theta 2, that is the second medium, is a conducting medium. Okay, second medium is a conducting medium. So if I have a second medium as conducting medium, that means the theta 2 of this is equal to 0, isn't it? So the theta 2 of this medium, that is the intrinsic impedance of the medium, is equal to 0. So in such a case, what will happen? Because theta 2 is equal to 0, the signal that you launch, the signal that you launch into the second medium, right? So if I, for example, if I launch it with obliquely, even the normal incidence also same thing. Okay, so let us say if I launch it with an oblique incidence of theta I, okay, if the second medium is a conducting medium, because the conducting medium will not pass the electromagnetic signal to pass through it, so right, it is very clear, we have to be very clear with this, right? Conducting medium will not pass the electromagnetic wave to travel through it. Okay, so remember this point. So because of this, what happens, the entire signal that you launched, okay, okay, at the right plane of incidence, so that entire thing will get reflected back into the original medium itself. Okay, so if I launch it properly, right, so if I launch it properly with a proper angle, then there is a total reflection that will happen, right, at the media boundary. So whenever I have a conducting media, right, so at the conducting medium boundary, there will be a complete reflection of the electromagnetic wave. Okay, so this point we have to be very clear. So using this point only, we are going to guide the wave through the waveguide. Okay, so transmit the wave, transmit the right electromagnetic wave through the waveguide. Okay, so how we do that? So let us, right, so what is a waveguide? Waveguide basically, waveguide has two conductors. There will be two conductors, right? So what I do, inside these two conductors there is air medium. So for me this is medium 1, and these two conductors that I have, these are the medium 2. Okay, so these are the medium 2. Now I launch the electromagnetic wave, right, into the medium 1 first. From the medium 1, now in this medium, this is my plane of incidence. This is the, right, medium 2 is this. So this is my plane of incidence, right? Now the electromagnetic wave coming from the medium 1 is hitting this, or it is launched onto the conductor media at an angle theta. Okay, understood? So I have a conducting media like this. This is my conducting media, right? This is the air. So the signal is getting launched onto here with some angle theta. Okay, now what happens, because the medium 2 is a conductor, so the theta 2 of this media is equal to 0. So therefore there will be a perfect reflection, that is a complete reflection of the electromagnetic wave into the first medium itself, that is into the halo space itself. Now this wave again will travel, right, again will travel onto the second conducting plate, and at the second conducting plate again the same action happens because the second conducting plate also has theta 2 is equal to 0. So there is a total internal reflection happening. So because of this, again the electromagnetic wave gets reflected back into the hollow space itself. So, right, it goes like this. Again, the same thing happens. So, in this way, right, the electromagnetic wave, right, travels through the waveguide, right, as a successive reflections at the boundaries. Okay, so this is the most important point. This is the principle of right operation of the waveguide. Okay, so the first point that we have to remember is, so at a conducting boundary, right, there will be a complete reflection of the EM wave. Why? Because the theta 2, the intrinsic impedance of the right conducting plate is equal to 0, and the conductor will not pass the electromagnetic wave through it. Okay, so it will not pass the electromagnetic wave through it. So right, there will be a complete reflection at the conducting boundary. Okay, now using this concept we are going to construct the waveguides. Okay, waveguides for transmitting the electromagnetic wave through, right? So this is the simple introduction to a waveguide and the principle of operation of the waveguide. Okay, so in the next class we will continue with the next topic.